Good day everyone, and welcome to our presentation. We are Shangjun Guan, Ziyu Pan, Jianzhong Feng, and Jia Zhou, here to discuss our research titled Joint Estimation of Identity Verification and Relative Pose for Partial Fingerprints. We've developed a novel approach that enhances fingerprint recognition by jointly estimating identity verification and pose prediction. Stay tuned as we delve into how this method outperforms existing techniques and opens up new possibilities in the field of biometrics. In this slide, we delve into the key highlights of our research. Our primary motivation is to enhance fingerprint recognition by exploiting the relationship between pose prediction and identity verification. We've identified a problem in the current landscape: the independent handling of pose prediction and identity verification. Existing methods may not fully harness the potential mutual benefits between these two tasks. Our solution is a novel approach that combines these tasks, aiming to improve the overall performance of fingerprint recognition systems. We believe that by jointly estimating these tasks, we can unlock new possibilities in the field of biometric security. Stay tuned as we delve deeper into our unique approach and its promising results. In this slide, we delve into the key insights of our research. We found that combining convolutional and transformer blocks in our network has distinct advantages. Firstly, this combination is highly effective in extracting local features and establishing global connections. This is crucial for our task of identity verification and pose prediction of partial fingerprint pairs. Secondly, we've discovered an exploitable promotion relationship between these two tasks. This means that the performance of one task can be enhanced by the successful execution of the other. This joint estimation strategy has significantly improved our results, reducing the equal error rate by up to 58.8%. These findings underscore the potential of our proposed CNN transformer hybrid network in the field of biometric authentication. Begin our frame. Frame title at key highlights. Begin itemize. Item: our novel CNN transformer hybrid network combines the strengths of both architectures. Item: this network performs two tasks simultaneously: identity verification and relative pose prediction of partial fingerprint pairs. Item: the process is divided into 4 stages: feature extraction, information interaction, identity verification, and pose prediction. Item: the feature extraction and interaction stages use convolutional and transformer blocks to extract and interact with the features of the fingerprint pairs. Item: the identity verification and pose prediction stages use the aggregated information to authenticate the fingerprints and predict their relative poses. Item: this joint estimation strategy has proven to be more efficient and effective than performing these tasks independently. End itemize. End frame. Begin our frame. Frame title at key highlights continued. Begin itemize. Item: information interaction. Inspired by natural image processing, transformers are utilized to capture long-range dependencies within and across paired features. This ensures sufficient information interaction. Begin itemize. Item: paired features are first biased with a sinusoidal positional encoding term, then flattened into 1D sequences and fed into stacked transformers. Item: the process includes residual connected multi-head attention, MHA, and feed-forward network, FFN, with self-attention and cross-attention sub-blocks. Item: a patch merging layer is incorporated for downsampling to refine features while reducing information loss. Item: positional encoding is applied again in the same way to further enhance the feature interaction. End itemize. Item: ablation study. The CNN Transformer Hybrid Series achieves the best overall performance. The joint estimation strategy significantly reduces the EER, proving the promotion relationship between pose prediction and identity verification. Begin itemize. Item: the additional alignment head can be removed during deployment to maintain matching speed. Item: a lightweight pre-training task can further improve performance at a small extra training time cost. End itemize. End itemize. End frame. Begin our frame. Frame title at key highlights. Begin itemize. Item: our training process uses a dataset called Hybrid DB1 A with a patch size of 160 by 160 and an initial learning rate of 1E3. The process runs for about 12 epochs until convergence. Item: we've conducted extensive ablation experiments, which show that a CNN transformer hybrid approach yields the best performance. Item: our joint estimation strategy significantly reduces the EER, proving a beneficial relationship between pose prediction and identity verification. We've proposed a lightweight pre-training task that further improves performance with minimal extra training time. Fingerprint recognition algorithms can be categorized into three types: key point-based, region descriptor-based, and pairwise correlation-based verification. End itemize, end a frame, .. Let's delve into the heart of our research, the finger puzzle method. As you can see in the figure, our method is a four-phase process, each phase represented by a different color. Our aim is to enhance fingerprint recognition by leveraging the interplay between two key elements: pose prediction and identity verification. We believe that these two elements can mutually benefit from each other, much like pieces of a jigsaw puzzle fitting together to form a complete picture. In essence, we're not just improving the way we recognize fingerprints, but we're also redefining how we approach the problem. We're moving away from independent tasks and towards a more integrated, efficient solution. Stay tuned as we delve deeper into each phase of our innovative method in the following slides. On this slide, we're diving into the heart of our proposed finger puzzle method. As you can see in the figure, our method is a four-phase process, each phase represented by a different color. We start with feature extraction, move on to information interaction, then identity verification, and finally pose prediction. Now, let's talk about the problem we're addressing. Traditional methods handle pose prediction and identity verification separately. They don't take advantage of the potential benefits that could come from a joint estimation. Our finger puzzle method, however, does exactly that. It combines these two tasks, aiming to leverage their mutually beneficial relationship. This is a key innovation in our approach, and we believe it holds significant promise for improving fingerprint recognition. Let's delve into the heart of our proposed solution, the finger puzzle method, as depicted in this figure. This innovative approach combines the strengths of a CNN transformer hybrid network and is divided into four distinct phases, each represented by a different color bar. Firstly, we extract features from the input fingerprint pair using convolutional blocks. These features are then concatenated and processed through transformer blocks for comprehensive information interaction. The final stages involve the use of this aggregated information to predict classification probabilities for authentication and regression values for relative poses. What sets our method apart is the joint estimation of these tasks, leveraging the mutually beneficial relationship between them. This method is particularly significant in scenarios requiring high-precision fingerprint recognition, such as unlocking mobile devices. Our goal is to provide an efficient and accurate solution to this problem, and the finger puzzle method is a promising step in that direction. Let's delve into the heart of our proposed finger puzzle method, as depicted in the figure. This innovative approach includes four distinct phases, each represented by a different color bar. Unlike previous approaches, which executed pose prediction and identity verification tasks independently, our method recognizes the potential mutual benefits of these tasks. In the first phase, we extract features from the fingerprint pairs using convolutional blocks. The second phase involves information interaction, both locally and globally, using transformer blocks. The third phase is identity verification, where we predict classification probabilities for authentication. The final phase is pose prediction, where we estimate regression values for relative poses. This joint estimation framework is a significant departure from traditional methods, and it's inspired by works on jigsaw puzzles. It's important to note that in most practices, only identity identification is necessary, so pose-related regression layers could be pruned to improve efficiency. In essence, our finger puzzle method is a novel, efficient, and effective approach to fingerprint recognition, offering a promising avenue for future research and application. Let's delve into our proposed method, which is visualized in this figure. We've developed a CNN transformer hybrid network that works in four distinct phases. The first phase, marked in red, is feature extraction. Here, our algorithm extracts features from the input fingerprint pair using convolutional blocks. The second phase, highlighted in gold, is information interaction. The extracted features are combined and processed through transformer blocks, allowing for both local and global information interaction. The final two phases, shown in blue and green, are identity verification and pose prediction. The aggregated information from the previous stages is used to predict classification probabilities for authentication and regression values for relative poses. What's unique about our method is that these two tasks are jointly estimated, rather than being performed independently. This approach allows us to leverage the mutually beneficial relationship between pose prediction and identity verification, much like solving a jigsaw puzzle. This method is particularly efficient as well, as the pose-related regression layers can be pruned when only identity identification is necessary, which is often the case in practice. Let's delve into the process of our proposed method, which we visualized in this figure. Our method is a four-phase process. The first phase is feature extraction, where we use convolutional blocks to extract features from the input fingerprint pair. The second phase is information interaction, where these features are combined and processed through transformer blocks for both local and global interaction. The third phase is identity verification, where we use the aggregated information to predict classification probabilities for authentication. The final phase is pose prediction, where we estimate regression values for relative poses. What sets our method apart is that these two tasks, identity verification and pose prediction, are jointly estimated. This is a departure from previous methods that performed these tasks independently. We believe that this joint estimation allows for a mutually beneficial relationship between the two tasks, improving the overall efficiency and effectiveness of the process. Moving on, let's delve into the heart of our proposed finger puzzle method. As you can see in this figure, our method is a four-phase process. Each phase is represented by a different color bar. We start with feature extraction, move on to information interaction, then identity verification, and finally, pose prediction. Now, let's talk about efficiency. In most practices, we only need identity identification, so we propose pruning the pose-related regression layers. This not only simplifies the process, but also significantly improves efficiency. In essence, our method is a blend of thoroughness and efficiency, ensuring accurate results without compromising on speed. This balance is what sets our finger puzzle method apart. Let's delve deeper into our proposed finger puzzle method. As you can see in the figure, our method involves four key phases, each represented by a different color. The process begins with feature extraction, followed by information interaction, identity verification, and finally, pose prediction. The strength of our method lies in its unique combination of convolutional and transformer blocks. This allows us to extract local features while also establishing global connections. This hybrid approach not only enhances the feature extraction process, but also promotes the interaction and utilization of valuable information. In essence, our method is designed to jointly estimate identity verification and relative pose of partial fingerprint pairs, a novel approach that sets it apart from previous methods. This joint estimation strategy has proven to significantly reduce the equal error rate, demonstrating the mutually beneficial relationship between pose prediction and identity verification. In the next slides, we will discuss the results of our comprehensive experiments and the potential future applications of our method. Stay tuned. In this slide, we delve into the existing fingerprint recognition algorithms. These can be broadly classified into three categories. The first is recognition based on key points, where unique identifiers in the fingerprint are used for recognition. The second is recognition based on region descriptors, which focuses on specific areas of the fingerprint. The third category is verification based on pairwise correlation, which uses a more detailed comparison method. Now, let's talk about the recognition methods. These methods store and compare generalized features of fingerprints. This approach enables efficient searches in large libraries of fingerprints. It's like having a vast library of books and being able to find the one you need in seconds. Remember, these methods are not mutually exclusive but rather complementary, each with its own strengths and applications. In the next slides, we will delve deeper into each of these methods and their applications. In our review of related works, we found that verification methods, which use richer information, are more suitable for high-precision requirements, such as unlocking a mobile phone. However, there are limitations in existing approaches. They often perform pose prediction and identity verification independently, which may not fully utilize the potential mutual benefits between these two tasks. Imagine if we could harness the power of these two tasks working together, enhancing the efficiency and accuracy of fingerprint recognition. This is the gap we aim to fill with our proposed method, which we'll discuss in the next slide. Stay tuned as we delve into our innovative approach that combines these tasks in a mutually beneficial way. Begin frame. Frame title our related works. Begin itemize. Item let's delve into the related works that have inspired our method. Begin itemize. Item we draw inspiration from the works on jigsaw puzzles 26, 28. These works have explored the concept of tasks having a mutually beneficial relationship, a principle we've incorporated into our method. End itemize. Item now, let's compare our method with a previous work. 8. Begin itemize. Item, our method differs significantly in how it represents the rotation relationship and describes the translation. This unique approach sets our work apart and contributes to its effectiveness. End itemize, end frame, This slide provides a brief overview of the related works that have influenced our method and how our approach differs from previous work. We've incorporated the principle of tasks having a mutually beneficial relationship, inspired by the works on jigsaw puzzles. Our method also stands out in its unique representation of the rotation relationship and description of the translation. Begin frame. Frame title advantages and future directions. Begin itemize. Item highlighting the benefits. Begin itemize. Item the CNN transformer hybrid network outperforms other methods, combining the strengths of local feature extraction and global connections. Item the joint estimation strategy significantly reduces the EER, proving the beneficial relationship between pose prediction and identity verification. End itemize. Item future work. Begin itemize. Item we aim to further improve performance on extremely low quality fingerprints and extend the method to single to multiple scenarios. Item we will explore the potential of a lightweight pre-training task to enhance the feature encoder's representation ability. End itemize. End frame. Begin frame. Frame title our results and future directions. Begin itemize. Item presentation of the results from the ablation study, highlighting the superior performance of the CNN transformer hybrid approach. Item discussion on the significant reduction in the equal error rate EER due to the joint estimation strategy. Item explanation of the benefits of the lightweight pre-training task in improving performance with minimal extra training time. Item brief mention of future research directions, focusing on improving performance on low-quality fingerprints and extending the method to single to multiple scenarios. End itemize. End frame. Begin frame. Frame title at the CNN transformer hybrid network. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC. Task underscore execution extracted underscore paper underscore data. 2405.03959 V1. Figures. 2405.03959 V1 figure 3:2.png. Captiona tinea. The four phases of the proposed algorithm. End figure. Begin itemize. Item delving into the technical details. Begin itemize. Item explanation of the four phases of the algorithm. Feature extraction, information interaction, identity verification, and pose prediction. Item discussion on how the algorithm extracts features from fingerprint pairs, interacts this information both locally and globally, and uses this aggregated information for authentication and pose prediction. Item emphasis on the efficiency of the proposed method, where pose-related regression layers can be pruned when only identity identification is necessary. End itemize, end frame, begin frame. Frame title at a hybrid network and its functionality. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC. Task underscore execution extracted underscore paper underscore data. 2405.03959 V1. Figures. 2405.03959 V1 figure 3:1.png. Captiona tinea. The CNN transformer hybrid network. End figure. Begin itemize. Item the hybrid network. Begin itemize. Item explanation of how the CNN transformer hybrid network extracts features from fingerprint pairs using convolutional blocks. Item description of how these features are then combined and processed through transformer blocks for information interaction. Item discussion on how the network uses this aggregated information to predict authentication probabilities and relative poses. End itemize. Item the joint estimation framework. Begin itemize. Item explanation of how identity verification and pose prediction are jointly estimated, leveraging their mutually beneficial relationship. Item mention of how pose-related regression layers can be pruned for efficiency when only identity identification is required. End itemize, end frame, begin a frame title implementation and results, begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, a SRC, task underscore execution extracted underscore paper underscore data, 2405.03959 V1, figures, 2405.03959 V1 figure 4:1.png, captiona tinea performance evaluation on hybrid DB A and B, end a figure. Begin itemize, item implementation details, begin itemize, item the training process was performed on the hybrid DB A dataset, using an initial learning rate of 1E3, cosine annealing scheduler, atom W optimizer, and a batch size of 128. Item a pre-training task was carried out for 300 epochs using a subset of 5,000 rolled images with random augmentation. End itemize, item performance evaluation, begin itemize, item comprehensive experiments on multiple databases demonstrated the effectiveness and superiority of our proposed method. Item the method showed cross-domain adaptability, performing well even without fine-tuning on different image sizes and datasets. End itemize, end frame, In this slide, we delve into the technical results of our research. As you can see in the figure, it provides an overview of our proposed finger puzzle method. This method is a novel approach that combines the strengths of a CNN transformer hybrid network for feature extraction and interaction. It enhances the attention and utilization of valuable information in the fingerprint recognition process. The finger puzzle method is divided into 4 phases. Each phase plays a crucial role in the overall process, contributing to the effectiveness and superiority of our proposed method. This approach has shown promising results in our comprehensive experiments on multiple databases, particularly with partial fingerprints. Our method also includes a lightweight pre-training task. This task is designed to improve the representation ability of the feature encoder by reconstructing enhanced images. This innovative approach has proven to be effective in our experiments, and we believe it holds great potential for future applications in fingerprint recognition technology. In our future work, we aim to further improve the performance on extremely low-quality fingerprints and extend the method to single to multiple scenarios. We believe that our finger puzzle method will significantly contribute to the advancement of fingerprint recognition technology. In our research, we've introduced a unique CNN transformer hybrid network. This network is designed to estimate 2 things simultaneously: the identity verification and relative pose of partial fingerprint pairs. This is a significant shift from previous methods, which perform these tasks separately. By combining these tasks, we're able to leverage the mutually beneficial relationship between them, much like solving a jigsaw puzzle. This innovative approach allows us to extract and interact with valuable information more effectively, leading to more accurate and efficient results. This is a major step forward in the field of fingerprint identification and verification. Begin a frame title at conclusions and remarks, begin itemize, item. Our novel CNN transformer hybrid network combines the strengths of both feature extraction and interaction, enhancing the attention and utilization of valuable information. Item. We've introduced a joint estimation strategy, which significantly reduces the EER, proving the beneficial relationship between pose prediction and identity verification. Item. An additional alignment head, which can be removed during deployment, ensures the matching speed is not affected. Item. We've also proposed a lightweight pre-training task that improves performance with minimal extra training time. Item. Our method outperforms previous approaches, as demonstrated by comprehensive experiments on multiple databases. Item. Future work will focus on improving performance on extremely low-quality fingerprints and extending the method to single to multiple scenarios. End itemize, end frame, This slide summarizes the key points of our research. We've developed a novel CNN transformer hybrid network that effectively combines feature extraction and interaction. This network introduces a joint estimation strategy, which has been shown to significantly reduce the equal error rate. demonstrating the beneficial relationship between pose prediction and identity verification. We've also included an additional alignment head, which can be removed during deployment to ensure the matching speed is not affected. Furthermore, we've proposed a lightweight pre-training task that improves performance with minimal extra training time. Our method has been proven to outperform previous approaches through comprehensive experiments on multiple databases. Looking ahead, we aim to further improve performance on extremely low-quality fingerprints and extend our method to single to multiple scenarios. In conclusion, our proposed method demonstrates both practicality and adaptability. We've designed it with real-world applications in mind, where identity identification is often the primary requirement. To enhance efficiency, we can prune the pose-related regression layers without compromising the performance. Our method has been validated through rigorous testing. We've conducted experiments on multiple databases, and the results have been promising. The CNN Transformer Hybrid Network, which combines the strengths of convolutional and transformer blocks, has shown superior performance. Furthermore, our joint estimation strategy, which simultaneously predicts identity verification and relative pose, has proven to be effective. In essence, our method is not just a theoretical concept, but a practical solution that can be implemented in real-world scenarios. It's a testament to the power of combining different techniques and strategies to achieve a common goal. Thank you for your attention. In conclusion, our proposed method brings several key benefits to the table. Firstly, it combines the strengths of convolutional and transformer blocks, allowing for effective feature extraction and the establishment of global connections. This insight could be instrumental for future research in the field, paving the way for more advanced and efficient systems. Secondly, our research has uncovered a mutually beneficial relationship between pose prediction and identity verification. This discovery opens up new avenues for enhancing the performance of fingerprint recognition systems. By leveraging this relationship, we can significantly improve the accuracy and efficiency of these systems. In essence, our work provides a solid foundation for future research in this area, and we look forward to seeing how these findings will be utilized to further advance the field of fingerprint recognition. Thank you. In conclusion, we have several exciting directions for future research. Firstly, we aim to enhance the performance of our method on extremely low-quality fingerprints. This will allow for more accurate identification even when the fingerprint data is not ideal. Secondly, we plan to extend our method to single to multiple scenarios. This will broaden the applicability of our method, making it useful in a wider range of situations. Lastly, our work indicates the potential for further advancements and applications of the proposed method. This opens up a world of possibilities for future research and development in the field of fingerprint recognition. Thank you for your attention.